clear.
It's loud and clear, right? Okay. So let me project my slide and yeah. Okay. It's visible, right?
Yes, Professor, it's visible.
So I think you can stream this thing session live, and we are good to start.
Done, sir. We can start now.
Sure. Okay. So good evening, everyone. Hope you had a good weekend and everything. Now, in the last session, the last Sunday session which we had, I found very few people attending the session. I think probably this was mainly due to the fact that you had some I mean, this fee which was happening. I mean, if my guess was correct, that was probably the reason. Many people missed out, but nevertheless, so what I'll do is, obviously, I can't repeat everything which we have covered in the last session. But what we were doing at the last part of the session was handling the way in which you could build the logic for splitting the decision tree and getting to a discussion, right? That is something which I'll do once again with you. And yeah, quickly we'll probably do the first part. And the part which was not done, obviously, we'll spend a great time on that. So here is some data set for your purpose, right? I think we had used almost the same kind of a data set when we had done the maze-based algorithm also, if you remember. One part of the problem was this same data set which we had, right? So again, as practitioners, you should be having the ability to solve a problem using multiple different techniques. And once you have solved the problem, you should be in a position of, obviously, to explain that why one method is better compared to the other. So some of the expectations from your end, and let's see how we can do this. Okay, so these are okay. So this is the data set, and here your outlook, temperature, right? Humidity, wind. These are some of the features which are there. And then at the end of the day, whether someone should go out and play golf or not, that piece is given, right? If you see the data, right, as you can see that there are 14 records out here, 14 records out here, and we need to build a solution based on the data which is given, right? Okay, so this is the example where to play golf based on temperature, humidity, wind, and outlook. And precisely, these are some of the questions which you should ask. That which feature to take first for building the decision tree, why take that particular feature first, and then what determines which feature to select. These are probably some of the things that we are going to discuss, right? Okay, so here are some quick statistics. If you see the data set, again, I think the slide is there with you. You will also be having the same data set in the slide. So here in are 14 cases, of which 9 says that, okay, go out and play golf. 5 cases say that, okay, don't go and play golf, right? So now, let's say that all those features which we are talking about are not here. In that case, we have in total 14 cases, right? And 5 of the 14 are saying not, or let's say no, and 9 of the 14 are saying yes. So if I go by majority, right, then if no other features are given, I'll probably say that, okay, yeah, go out and play golf, right? Based on the majority, based on the majority. Let's say you have not created any model to start off with, based on the majority, because again, I see more of my records. They are saying that, okay, go out and play golf. Could also say that, okay, if I don't have any further information to take the decision, just go out and play golf, right? That will be my solution. But the thing is that there are so many features which are given. So what we need to do is we can probably try to break these training examples into smaller and smaller subsets, right? And incrementally develop the tree, right? So how we can do that? For example, the first variable which we can try and test is this temperature. Right? If we go back, you'll find that temperature, there were so many values, right? So temperature, hot, mild, cool, all those things are there. So let's say I take the temperature, and let's say if I split my tree based on temperature, so if the temperature is less than mild, then go and play golf. If the temperature is greater than equal to mild, don't play. Right? Now, if I get something like this, my problem is solved. Because whenever someone asks me to take a decision whether to play golf or not, I'll simply ask, what exactly is the temperature outside? If the temperature is given as less than mild, fine. We'll suggest that, okay, just go and play golf. If the temperature is more than mild, our suggestion would be don't play golf. Right? Here comes some kind of a challenges. So let's say that when the temperature is less than mild, the playing golf part is pretty consistent. When the temperature is less than mild, everyone is saying that, okay, go out and play golf. Right? But the case when the temperature is more than mild, greater than equal to mild, that is when we have some kind of ambiguity. Right? And again, when I'm saying ambiguity, that is coming from the data. It's not coming randomly, it is coming from the data. So let's say here, at this point in time, let's say there are 4 saying play and 6 saying don't play. Right? So then I don't have a homogeneous decision. Here, since there are 10 records, here you see that this example, 10 records, of which 6 are saying no play, don't play, and 4 are saying play. So I'll go by the majority and I'll say that don't play. But again, you see 4 on one side and 6 on the other side. Not a very good decision that we have taken, right? Can we look for some other features? Yes. Maybe humidity is the feature which we can look at. So if the humidity is normal, yes, go and play. Humidity is not normal, don't play. This time probably my problem is solved. So here are 4 records and here are 6 records. So we started with 14. Initially here was 4 and here was 10, and then this 10 was split once again into 4 here and 6. Right? Then my problem gets solved, or probably maybe I have made a little mistake. This one. It is 5, and this one is less than 9, and the 9, 4 are saying yes. Now it will be better. Yeah. 9 and here it will be 5. Yes. Okay. So then I have solved the problem. I can exactly say that when to play golf and when not to play golf. Now the question is that how do I know that I'll have to do splitting based on temperature or this humidity? Why not the other ones? Why not the wind, outlook, right? How do we find these important variables for doing the split? That is what we are going to discuss, right? And so many techniques we are going to discuss today, right? Please pay attention. This is not given in most of the books or again in your learning materials, but this is pretty important from your knowledge perspective. There's one algorithm that you should learn properly. I think this is the algorithm. Right? As I said, that this algorithm is easily explainable. You can do a beautiful visualization chart from it. Right? So yeah, pay attention to it. Okay. So what we are going to use is something called as a divide and conquer method, right? And this divide and conquer is going to be consistent across all techniques where decision tree is involved. So for decision tree also, there are so many techniques which are out there, right? But all these techniques will employ some kind of divide and conquer mechanism, right? Let's see how. So first, what we will do is we'll select some of the features to do the tree splitting. That's the first thing that we are going to do. And then once we select that particular feature, we'll create branch for each of the possible outcomes, right? And then what we do is that we keep on doing this split again and again until and unless there are no more inconsistency in my decision. No more inconsistency, right? Let's see how. So first, what I'm going to talk about is a method called tide. We have already done this in the last class, right? I'll not spend too much time explaining it, but I'll quickly go through this part. So again, tide algorithm, it was proposed by Cass in 1980. It stands for chi-squared automatic interaction detector, right? And this is the formula for this chi-square, right? So chi-square is given by observed minus expected whole square by expected sum of that, right? You might be wondering that what is this observed expected? Let me come to that. So here was my data, which is there. So if I go back to my data, yeah, this was the data. So here I had 9 cases for play, 5 cases is not play, right? If all the features had no infraction or no effect on the playing decision, ideally I should be having 7 play and 7 not play. And let's say none of these features are useful to make my decision. So ideally I would be having 7 play and 7 don't play. Net resulting, what will happen is that if I have to take a decision, because there are equal number of cases in play and don't play, I'll not be able to take any decision. That is what is going to happen, right? And that is the one part which we would like to change, which we would like to break. How? Let's see. Okay. So, yeah. Let's take each and every variable. Let's take the first variable, which is humidity. For the humidity, what is happening is that I'm seeing that in total, I had 14 records, right, which you can see out here. Of these 14 records, 7 are saying high and 7 are saying low, right? Now that's also a problem, right? So I have humidity and 7 are saying high, 7 are saying low, right? Now what is the split of my decision between this high and low? So see this one, this particular part. So here, of the 7 records, 3 are saying yes and 4 are saying no. Difficult to take a decision, right? Almost same, almost pretty balanced. But take the case here. So here I have once again 7 records, but 6 are saying yes and 1 is saying no. The decision is much more skewed for this yes case, isn't it? So now let's assume that this high or low didn't have anything to do with my decision. So 7 records are there. I'll expect that 3.5 will go for yes and 3.5 will go for no. That is expected. Had this particular variable didn't have any kind of a effect on my decision. Same for this one also. 7 records are there. 3.5 should say yes, 3.5 should say no. Now, you might question that, Professor, I mean, how can I have our decision? Right? I'm with you. I'm with you. So this is this doesn't make any sense actually in the real context, but again, mathematically, it makes a complete sense. Right? Mathematically, we can have our decisions. Right? Okay. So this is my total case, and this is my expected value. So now I'll apply the chi-square formula. So observe is the actual value, right? So for the yes case, 3 is the observed, expected is 3.5. So 3 minus 3.5 whole square by expected 3.5. This will give you 0.267. For the case of no, 4 minus 3.5, right? So observed minus expected whole square divided by 3.5. Once again, it will give me 0.267. Okay, come to the case of this low. So 6 minus 3.5, right? Whatever is the value, right? That will be 2.5. 2.5 whole square divided by 3.5. This is what it will give. And then this is 1. 1 minus 3.5. Once again, it is minus 2.5 whole square divided by 3.5. This is what is the value you get. Now, for this entire node, humidity, if I split by humidity, let me compute the aggregated chi-square value. This is the aggregated chi-square value for this humidity part. Right? One thing which I'll bring your attention is that, see here, I have 6 cases going for yes and 1 case going for no. The decision is treated towards this one, right? This yes case. I get a high chi-square value, both for the yes as well as the no case. Right? But see here, the decision was pretty much close by, and here the chi-square value was also lower. Right? That's just an observation which we made. So let's go and look into the other cases. Okay. Let's go for the wind part. So in the wind, once again, I have 8 plus 6, 14 cases, of which 8 are weak and 6 are strong. So 8 cases, 2 decisions I have, yes, no. So ideally it should be split equally between the yes and the no. So this is my expected value. So 8 by 2 decisions, yes and no, 4. Right? Now let me find out the chi-square values. So 6 minus 4 whole square by 4, this gives 1. So 2 square, which is 4 by 4, 1. And this one, 2 minus 4 whole square. Minus 2 whole square, that is 4. 4 by 4 is 1. See out here. So for the case of this wind storm, I had 6 cases, of which 3 said yes and 3 said no. So 2 decisions, 6 by 2 is 3. So observed is 3, expected is also 3. 3 minus 3 whole square is 0. So 0 by 3 is 0 once again. And here also 3 minus 3 whole square is 0. So 0 by 3 once again is 0. So here, when the wind was strong, I had 6 cases. 3 said yes, 3 said no. So which means this particular strong part does not contribute anything to my decision. Because whenever wind is strong, I'm equally at question that whether it should be yes or it should be no, right? Whether I should go out and play and don't go out and play. So chi-square value is coming out as 0. Whereas here, 6 and 2, much tilted for this side, I get a positive chi-square value, a chi-square value of 1. So again, once again, when we add this up, this gives the value of 2, right? So like this, we are going to do for everyone. So this is for the case of this outlook, right? So outlook, sunny, overcast, rain. Once again, the same drill. So here I had 5 cases, 4 cases, 5 cases. So 5 total number of cases, 2 decisions. So expected 2.5. 4 total number of cases, 2 decisions, right? So 4 by 2 is 2. And then once again, 5 cases, 5 by 2, 2.5 is expected, right? So observe minus expected whole square by expected, right? These are the different chi-square values you can get. Right? Once again, I add it up, I get it as 4.092. And lastly, the temperature, this is what I'm having from the temperature. I add it up, this is what I get. Now, I have got this chi-square values for all the different variables. My question to the class is that, what do you think? A higher chi-square value that is useful for taking a decision, or a lower chi-square value is useful for taking the decision? What is your take? Okay, some answers are coming in. Shika is saying higher value. Sambit is saying higher value. Good, good. Sanyam is saying higher value. Exactly. So here you see, right? You're exactly correct. Here you see that I had 3 cases for yes, 3 cases for no. So my chi-square ended up to be 0, a value of 0, right? Which means I can't take any decision on this. Whereas if I had higher values for everyone, right, then probably it was easier. So what I'm doing is that I'm tabulating all the values. And these are the chi-square value for each of these cases: outlook, temperature, wind, and humidity. You can see that outlook is having the maximum chi-square value. So this is the first variable based on which I tested, right? Okay. So now I split the data based on this outlook value, right? And here you can see that when it is sunny, there are 3 no, 2 yes case. When it is raining, there are 3 yes, 2 no. And when it is overcast, 5 yes. So for the overcast case, my decision has become completely homogeneous. I don't have any kind of ambiguity in this. But again, for the case of sunny and for the case of rain, still some ambiguities exist. I need to mitigate this ambiguity, right? So again, we'll go for the next step. But my question to the class once again. So for the outlook overcast, as you already see, that if the outlook is overcast, the decision is simply go out and play golf. No problem with that. What will happen for the outlook sunny? Let's say I keep this table as this thing. What will be my decision when the outlook is sunny? Yeah, class, what will be my decision when the outlook is sunny? Let's say I keep the decision tree as it is, like what you're seeing on the screen. So when the outlook is sunny, what will my decision be? Anas is saying no, and yeah, no without considering any other feature. Anshul is saying no, Sanyam is saying no, and that's the correct answer, right? Because why? See here, if you see, you are having 5 records, right? Of which the majority goes for no, right? Had there been 6 records and 3 yes, 3 no, then I would have been in trouble, right? Because again, difficult to take a decision. But here, still, you can argue that, sir, again, it is just a difference of 1. But again, if I just go by the majority is saying no out there. So for the outlook study, if I just don't do anything else, this is what my decision is going to be. For the other case, the outlook has rain. The outlook has rain. 3 yes, 2 no. So my decision is going to be yes out here. Okay. Second question to the class is that if I keep my tree at this particular stage, I don't split it further, right? What will be the accuracy of the overall tree? What is going to be the accuracy of the overall tree? If I use this decision tree to take my decisions, what will be the accuracy of the overall tree? Again, Shikha is saying low. Again, Shikha, this is a class of data science. We need some numbers, right? We need some numbers. Not some kind of a speculation, but some numbers. Okay, what will the accuracy of this particular tree? Anyone? Anyone? Sanyam is saying 4 by 4 plus 2 by 5 plus 3 by 5. Okay. Okay, we'll come to that. Shika is saying without test data, how can we calculate accuracy? You can do the calculation based on the tree which we have right now, which we are having right now, right? See, there's no one who's saying that you only need to have the metric on the test data. You can do the metric on the training data also. So though that's not a usual practice, but yeah, you can do on the training data also. So let me show you how. So here I had 14 records in total, of which you will find that 5 record went here, 5 record went here, and 4 record went here. Right? In these 4 records, my decision will be yes, and that will be the correct decision, right? So here, of the 4, this 4 will be correctly identified, right? Okay, come here. So here I have 5 records. So 5 records, of which 3 are correctly identified, because again, my decision here based on the majority will be no. So only 3 could be correctly identified. This 2 will not be correctly identified, right? So here my accuracy will be 3 by 5. Same case out here. So here the majority is yes. So I'll also say my answer is yes. So 5 records I had, 1, 2, 3, 4, 5, of which, right, 3 would have been correct and 2 would have been misclassification, because this 2 no also I'll say the decision as yes. So here also 3 by 5. So my overall accuracy would be, I had 14 records. So 5 by 14 into 3 by 5. Plus here I had 4 records. So 4 by 14 into 4 by 4 or 100%. Plus once again 5 by 14 into 3 by 5. So whatever it is, that is going to be my overall accuracy. Otherwise, what you can do is another simpler method. You had 14 records. So here 2 will be misclassified. Here 2 will be misclassified. So which means of 14 records, I'll have 10 correct classification and 4 misclassifications. So 10 by 14, whatever that comes out, that is going to be the accuracy of this particular decision tree. Right? Got the point? Shikha, doubt cleared? I think one person only gave the answer correctly. Hari gave the correct answer to us. Right? So Hari said the answer would be 10 by 14, and yeah, that was the correct answer. Okay, let's move ahead. So once again, see, here my problem is solved, right? All consistent, no issues. Problem is here and here. These are the places where we have some problems. So let's solve those problems, right? So what I'll do is that, okay, there's some questions. Somebody is saying not able to send the chat to everyone to see everyone's answer. I think let me check if the upgrade person is there or not. No, I don't think the upgrade person is here. I think the person has left, because they are only having the this thing, the rights to make sure that everyone is able to see, right? Unfortunately, that person is not there. Okay. Okay. So now, as you can see, that I'm still making some errors whenever it comes to this sunny or the rain branch, right? For the overcast branch, I'm good, not making any problem, right? Not having any problem. So let's look into the divide and conquer once again, and let's take the outlook sunny. So for the outlook sunny case, this is how my data looks like, right? And as you can see, that 3 no and 2 yes, right? So I had this 1, 2, 3, 4 features, of which this particular feature I don't need to take into account, because again, it's all sunny, it doesn't contribute, right? So this feature is not required. I'll probably work on these 3 features, right? Even before I go and work on these 3 features, let's see the data. Can you tell me that of these 3 features, temperature, humidity, and wind, which one will be more important for my decision? What do you think? Sanyam has given some answer. Okay, let me see the others answer as well. Shashwat is saying temperature. Sambit, okay, is saying humidity. Sanyam had said humidity. Let's see. Shukanta is saying humidity. What are the others? What about the others? Anshul is saying humidity. Okay. What are the others? Shikha is saying humidity. Okay. One more answer, and I'll probably go for the explanation part. One more answer, and then probably I'll go for the explanation part. One more answer. Rahul is saying humidity. Good. So my majority is saying humidity, and the answer is humidity. Exactly, the answer is humidity. Why? Okay. Once again, here, see, my objective is to make this homogeneous or consistent. If you see, for the other cases, see here, if I split based on temperature, so two cases of hot, which are saying no, which is fine, homogeneous for hot. For cool, only one case, so yes, that is homogeneous. Look into this one, mild. Mild one, mild two, but so mild one is saying no, mild two is saying yes. Okay, still it will not be homogeneous. Let's take the case of the wind. So wind is weak. Let's take the wind weak, 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 weak. Two no, one yes. Wind strong, one no, one yes. I'm not able to come to a decision. But come to the case of humidity. Whenever the humidity is high, always it points to no. And whenever the humidity is normal, always it is pointing to yes. Problem solved, right? So if I split it based on humidity, then maybe that will help me get to a homogeneous kind of configuration, right? See, here you have only had a small number of records. 5 records you had, you could immediately see and make the decision. But let's say that if we don't have humidity, let's say it was only the temperature and the wind which was there. Now, if you have to take a decision, right? Can you take which one is the one which will be more preferred? It becomes difficult, right? See, our human brain, what happens is that when human brain sometimes works, human brain generally works well when it is very objective, right? So here the humidity high was no, all the cases no, humidity normal, all the cases was yes, right? It was a very binary kind of split. Your brain could figure it out. But whenever there are mixes and matches, right? So whenever the decisions are not very straight, that is when you start facing problems, right? Got the point? Let's move ahead. So what we'll do is, once again, we'll take it mathematically, right, rather than doing it by intuition. So already most of you had given the correct answer by intuition only. But again, once again, we'll go via the chi-square path, right? So for the case of high, I had 3. For the case of normal, I had 1, 2. So 2 decisions. So expected is 1.5. Here 2 decision, expected is 1. So once again, we'll find out the observed minus expected whole square by expected, observed minus expected whole square by expected, right? So this is for the humidity, this is for the wind, and this is for the temperature. Once again, I'll tabulate the chi-square values, and as you guys have found out, humidity is the maximum, so we will split the tree based on this humidity. So this particular branch, sunny branch, gets split based on the humidity. So humidity high, no. Humidity normal, yes, right? So already I have ensured that there is homogeneity for outlook overcast and outlook sunny through the humidity part. Okay, my question to the class, at this stage, right now at this particular stage, what is the accuracy of this setup? What is the accuracy of this particular setup at this point in time? Accuracy? Accuracy? Some answers are coming in. Sukanto is saying 100%. No, Sukanto, that's not the correct answer. Accuracy of the entire setup right now. See, still you have on the right hand side the rain part, right? So I've given you the hint. Now can you tell me what exactly is the accuracy of this configuration? Of this configuration at this point in time. Shikha is saying 12/14, and that's the correct answer, right? Sambit is saying 0.33. Sambit, that's not the correct answer. The correct answer is 12/14. How? Right? So here you see that 5 records, all the 5 correctly identified. 3 records, all the 3 will be correctly identified. 2 records, all these 2 will be correctly identified. But see out here. So here I have 3 yes and 2 no. If I have to take a decision based on this particular node, I'll go by the majority and it will be yes. So if I give the label as yes for this particular node, what will happen is that this 2 no it will be misclassified. So from 14 records, 2 misclassification divided by total number of records. So 12 by 14 is going to be the accuracy of this configuration at this point in time. Okay, so Sanyam has given a very interesting this thing, right? So Sanyam, what I'll do is I'll put your answer on the screen for everyone, right? So here you see I had 14 records. 4 here, 3 here, 2 here, and 5 here. So here 100%, 100%, 100%. So 4 by 14 into 100% plus 3 by 14 into 100% plus 2 by 14 into 100% plus here 5 records were there, 5 by 14 into, so here 1, 2, 3, right? So 3 out of the 5 would be correct. So 60%. Whatever that comes out, that's the answer. Finally, it will come out to be the same as this 12 by 14. That is the accuracy of this particular decision tree. I think it will be 85 point something, right? So if you remember the earlier configuration, we had 10 by 14 as the accuracy, which would be something around 71.4%. And here, this will be something around 86.6%, right? So by doing this additional split, what we have done is we have ensured that the accuracy, prediction accuracy of this tree goes up, right? Now still this rain part is there, right? Still we can ask more questions. And again, I'm not going for the process. So this is for the rain part. And you can see that the wind is coming as the most important variable, right? With the maximum chi-square value, right? I'm not showing you the calculation again. So now I split on the rain branch based on the wind. So wind weak, all yes, wind no, all no. Okay, Shikha is having some question. Yeah, let me come to Shikha. Yes, Shikha.
Yeah, thank you, sir. Sir, here the question that I have is, as you're splitting from sunny to humidity, so you're taking all the records that have right. So I'm wondering whether you take a subset of who are saying yes or no, or you're taking all the records that are saying yes as well as no.
Go back. I think you missed out some part. Okay. So this was my earlier configuration. This was 5, right? And here overcast, already all decisions are homogeneous. I don't need to take anything. I need to probably do something for this sunny and this rain.
Oh, sir, here is a question actually. Yeah, here is a question that I probably should have asked here itself. So actually, as a data set, we have 14 records.
Yes.
Totally, right? So all the 14 records will have some information about all the 3 variables, right? Sunny, overcast, as well as rain.
Right.
And then, so I don't understand why sunny has only 5 records. What is this subset is what I've completely missed out on. Oh,
so let me go to the basics. Okay.
Oh, sorry,
so this is how the data was looking like. This is how the data was looking like, and here for the feature outlook we had sunny, overcast, and rain. So all the 14 records had some records for sunny.
Oh, I see. Okay, you took only one. Okay, out of those you took only one class. Okay, so you can move forward now. Sorry about that.
No, nothing.
No, actually, I was confused about whether you divide the trees based on yes or no, and then take different features. But it is the other way around.
It's the other way around. It's the other way around.
Yeah. Okay.
So here, what we did was for the sunny case.
Yeah, right? Yeah. So I've got it right. You can move. You can move to the.
Now you have these 5 records.
Yeah.
And based on these 5 records, once again, we found out that of this, because this is uniform.
Yeah.
Taking decision based on this. of the other three, which one would be important for taking my decision, right? So that's how we do it. Right?
Yes, understood. Thanks, sir.
Okay. So now my decision tree has become completely homogeneous. If you look into the accuracy, 100% accuracy in prediction at this point in time, right? So that was the way in which what we did was we ensured that we create tree where we are exactly able to take our decision. Now, one problem which you can see out here is that, see, in this particular branch, only 2 records. See this particular branch, only 2 records. In the worst possible case, what might happen is that this leave nodes. So again, these are the terminal nodes where the decision is homogeneous. Those are the terminal nodes, right? Decision is homogeneous. So sometimes you might come to a situation where the terminal nodes like this are all having, let's say, 1 records. So which means that, let's say, so our data set has only 14 records. So let's say if you are having 100 records, the terminal nodes or the leaf nodes are having 100 leaves. So which means that there's no model which has been built. Basically, what you have done is you have just memorized the values, right? Which is bad. And this particular phenomenon is actually called the overfitting of the tree. Overfitting, right? Okay. So how long to keep splitting? One is leaf nodes are pure, only 1 class remains. We have exactly done that. 2 is a maximum depth is reached, or 3 is a performance metric which has been achieved. So let's say that in this problem, I had specified that, okay, come what may, I am not going to create a very deep tree. I'll have decision tree which goes only up to 1 level. If that would have happened, I would have stopped growing the tree at this particular level only. So outlook, sunny, overcast, rain, I would have stopped it there only. I won't have splitted the tree further. Right? That can be my one strategy for determining how long to split. The other strategy could be that I look into some kind of a performance metric. And in this configuration, because my leaf nodes are completely pure or homogeneous, right? So here I have 100% accuracy, right? 1 class remains, it's 100%. Here, maximum depth we have already discussed. Otherwise, this performance metric is achieved. So let's say I had given my performance metric as, let's say, 80%. 80% accuracy, I'm good. When we had done the first level of splitting, if you remember, it was 10 by 14, something around 72%. My performance metric is not reached. But when we split the sunny part of the record, our accuracy changed to 12 by 14, which is more like 86%. I reached my performance metric and I'm good. So the third part, this particular part, I probably won't have split it because I have reached the performance metric which is there. Okay, so Shikha is having a question: is there a minimum value of instances that terminal node should have for it not to be an overfit model? I'm not sure of the question. Minimum value of the instance. I mean, I assume that when you're saying minimum value of the instance, you're saying that the minimum number of records. Is that what you're meaning? Okay, we'll come to that. Nice question, right? We'll come to that. Okay. So here, leaf nodes are pure, 100%. Maximum depth is reached. I don't know what performance metric it will give me, right? We'll have to see at that particular point. And a performance metric is achieved. So this is where performance metric is achieved, right? 72% have not achieved. 86% I have achieved this 80%. So we are good. We are good, right? Okay. But again, this is the final decision tree where we have ensured that leaf is homogeneous or pure. This is what we have ensured out there, right? Very good. Let's move ahead, right? So this kite or the chi-square interaction detection That was just one of the ways in which you could have the splitting. Right? Let's see some more. Right? How long to keep splitting? Until leaf nodes are pure, as we said, maximum depth is reached, performance metric is achieved. Right? So, building the best decision tree. Right? See, one thing which you have seen is that in the process of building the decision tree, our approach has been a very greedy approach. Why I'm saying greedy? Because we are evaluating each and every feature and trying to find out whether this feature will be important for doing the split or not. That we did using the kite. There are other methods also which satisfies the same objective, and that's what we are going to do right now, right? So splitting the decision tree. Already the kite we have discussed, but we are going to split the other ones. So these are some of the ways in which you can do the splitting, right? We have already discussed this one, chi-square, already discussed this one, right? Let's look into this one, classification error, Gini index, and entropy, right? So by the way, let me just give you an idea. This chi-square, it comes from statistics. Classification error, it comes from probability. Gini index, actually it comes from econometrics. And finally, this entropy, it comes from your physics. Right? Now, you might be questioning, Professor, how come this different metric coming from different field of science are being used out there? Right? That might be a question. See, at the end of the day, what we are interested in is something called homogeneity, right? Something called as homogeneity. And what is this homogeneity? What is when I have reached some kind of a stable configuration, right? Now, the stability has different kind of interpretations in all these different cases. So, for example, somebody just said that this entropy, which I said is physics, that comes from thermodynamics, right? So again, let me just unmute Sambit. So Sambit, can you help explain that what exactly is entropy in the thermodynamics part? How we use it? Yeah, Sambit.
So I'm audible.
You're audible. Perfectly audible. Tell me.
So it is like if I remember vividly, actually, I read
fine.
it in.
That is fine.
Yeah, but entropy is like you can say the degree of disorder or something, like if in
Exactly.
a chamber there are randomness of some atoms and there, then the degree of that disorder and randomness that in the system, that's called entropy.
Exactly. Yeah. And if there is a high entropy, what does it mean?
High means there is like you can say, I think the randomness is more in that atom or something like that.
Exactly. And low entropy means lesser, right?
Yeah.
So here, if you remember, right? Fine. I'm just muting you once again. Okay. So for the case of this entropy, if you remember, right, for other people who just has some memory of what was being taught, if you heat an atom, right, or a metal, the metal becomes hot, isn't it? So when you heat, what happens is that the internal kinetic energy, it increases, and the atoms, they collide against each other, and that is how the heat gets generated. Whereas if you cool it, what happens is that this randomness or this striking of the atoms against each other, that becomes low, and in the process, what happens is that the temperature is low, right? So this entropy, it comes from physics, as I said, and these are some of the ways in which we can measure the impurity. So let's quickly, it's the time, it's almost close to 8. Let's quickly just piece up a little bit. I think now you have got enough idea, right? Okay, on the left hand side, you have this totally pure part. On the right hand side, it's an impure thing, right? Left hand side, why pure? Again, you have see all this green particles. Right hand side, impure. Why? Along with this green, right? Along with this green, you also have this blue and the red, right? So just think of the water filter in your home. In this water filter, what happens is that you measure something called as a TDS, isn't it? TDS, total dissolved solvent, right? And if the TDS is high, that water probably is not very good for drinking. So then what you do is you probably use some appliance like this water purifier, right? This iron softener, all these UV pieces, so that you can bring out the TDS down, right? So these filters are there, right? And each of these filter, they are having some particular task. So one filter is probably there for soaking the big particles, right? One filter is there, which is basically the iron guard, right? So like this, you have the different filters. Right? Similarly, we are going to use the same principle in decision tree also. We are going to use these filters so that at the end of the day, we get pure nodes, right? Just to give you an idea, if you somehow, I mean, there is a outlet which comes from your water purifier. If you check the impurity of the water which you had initially, and the impurity of the water which comes out from the waste outlet, you find that the impurity is more out there, right? And obviously, the water which you drink, that will be having a lesser impurity, a lower TDS value, right? Okay, let's move ahead. Remember this thing, for a pure or homogeneous data set, the impurity value becomes 0, right? This is a little bit contrast to the entropy part which we had learned, to the chi-square part which we had learned. So there, the higher chi-square value was better, right? But here we'll see that how to measure the impurity part. The impurity, lower the impurity, better it is. Okay, the first one which we'll take is something called as a classification error. So here you see that there are 8 plus 4, 12 records. 8 yes and 4 no, right? 12 records are there, 8 yes, 4 no. So classification error is 1 minus maximum of the proportions which are there. So 1 minus maximum of 8 by 12 and 4 by 12. So which means 1 minus 8 by 12 is 4 by 12 is equal to 1 by 3 equal to 0.33. There is a classification error at this particular node. See out here, I have 4 records, 2 are saying yes and 2 are saying no. See, by the way, whenever you are applying any decision on this decision tree, always it is with regard to your target variable. I think that was the part where Shikha got a bit confused. The splitting and all these things, what you're doing, you are basically taking into account, measuring how the target variable is distributed, right? So here, rather than this 2 yes, 2 no, let's say if it was 4 yes out here or 4 no, then this was homogeneous. This wouldn't have any impurity, right? See, for the case where, let's say, it was perfectly homogeneous, here, let's say 4 yes was there and 0 no, 4 yes, 0 no, then your impurity would be 1 minus maximum of 4 by 4 and 0 by 4, which is 1 minus 4 by 4, which is 1 minus 1, 0. So completely pure node, completely pure node. But again, here we have things the other way around. So here we have 2 yes, 2 no. So 1 minus maximum of 2 by 4, 2 by 4, which is 1 minus 2 by 4, or 1 minus half is half. Right? So that is the impurity here, 0.5. This was 0.33. And here, 1 minus maximum of 6 by 8 and 2 by 8, which is 1 minus 6 by 8, which is 2 by 8, which is 1 by 4, equal to 0.5. 0.5. Okay. My question to the class, at the root node, the impurity value was 0.50, whereas on one side you got it as 0.5, the other side you got it as 0.25. Is it a good split or a bad split? And how you're going to measure that? Has our split been successful or unsuccessful? Right? And how you're going to measure that? Okay. No answer, but again, that's fine. See, herein comes a concept called reduction in impurity. Reduction in impurity, right? Reduction in impurity and how it happens. So let's say you had 8 yes cases and 4 no cases, right? Initially, you saw that this impurity was 0.33. Now, after doing the split, let's say I have here 4 no cases and here all the 8 yes cases, right? As we saw that the impurity value for homogeneous things will be 0. Here also homogeneous, it will be 0. So what I'm going to measure is something called as a reduction in the impurity. So here 12 records I had. So 12 of the 12 records had overall impurity of 0.50. Right? When I had split based on temperature, 4 of the 12 had an impurity of 0 plus 8 of the 12 had a, let's say, impurity of 0. So then my overall reduction in impurity was 0.50. So what I'm going to measure is that by doing a split on some of these values, what has been my overall reduction in impurity, right? So let's take the original values which we had out here. The original values was 0.33 out here, 0.50 impurity out here, and 0.25 impurity out here. So my reduction in impurity would be 12 by 12 into 0.33 minus, so here 4 by 12 into 0.50 plus 8 by 12 into 0.25. So whatever that value comes out, that will be my reduction in impurity. So again, so here the values are calculated. So this part impurity was 0.5. On the right hand side, impurity was 0.25. So this is the overall reduction in impurity, which by the way comes out as 0. What does it mean? It means that by splitting on this temperature, whatever was the impurity earlier, my overall aggregate impurity remains the same, which means that in terms of helping me take the decision, this particular node, this particular split probably is not that much efficient for helping me take the decision. That is what it means, right? Okay. So here, at least with classification error, we could not proceed much. Why? Because again, it has given me a 0, right? Can we try out some different metric? Yes, some different metric are there, right? So that is when we'll come to this entropy, right? So entropy, as I said, comes from the domain of physics, computes the homogeneity or the amount of randomness in some particular matter or state out there. Entropy typically belongs to between 0 and 1. 0, all members belongs to the same class. 1 means that there are probably equal number of positive and negative examples, right? So let's see how we are measuring the entropy. This is how you measure the entropy. You sum up all the proportions and log to the base 2 of that particular proportion. So this one, the entropy would be 8 by 12 log of 8 by 12 plus 4 by 12 log of 4 by 12. Right? By the way, why there is a minus sign in front? You see this minus sign in front. Why? Why minus? Anyone? Anyone? Why minus sign? Just common knowledge, nothing to do with the data science, nothing to do with decision tree. Right? Just some common principle. Anyone knows? Okay, I'll tell you. If you take log of a fraction, yeah, I think Shashwat has given me the answer, right, Shashwat? So log of a fraction basically gives you a negative value, right? So I'm putting a negative sign in front so that I can get a overall positive value. That's the reason, nothing else. Okay, so this is the entropy at the root node, right? So this is the entropy, comes out as 0.9183, right? 0. So 8 by 12 log of 8 by 12 and 4 by 12 log of 4 by 12, 0.9183. That's at the root node. Let's see the left hand side. Here I had 2 yes, 2 no, like equally split between the two. So here 2 by 4 log 2 by 4 and 2 by 4 log 2 by 4 again. Maximum impurity, right? Records are equally split between the two different classes, maximum impurity. And if I see on the right hand side part, on the right hand side, it is 0.8113. So 6 by 8 log 6 by 8, 2 by 8 log 2 by 8, right? And if I look into the change in entropy, so this is the one which is there at the root. This is the left hand part. This is the right hand part. So root minus left minus right. This is the change in impurity which I get when I had used the entropy as my metric. Right? Okay. So the question is that why this works with entropy but not with classification error. Because classification error, I found that I have reached a state where I can't split it further. Right? That's what I saw with this classification error. But with entropy, I was actually able to split. But again, by the way, once again, the same question remains. Professor, how did you know that I have to use the temperature? Again, this is just an example which we have taken. In the real case, what you have to do is that you have to find this reduction in impurity part for each and every feature. So temperature is a feature, right? Your outlook is a feature, humidity is a feature, wind is a feature. For each and every feature, if you do the splitting, you have to find out that what is the reduction in impurity which happens, right? Wherever you get the maximum reduction in impurity, you take that variable for splitting, right? Okay. For the part of this classification error, if you remember, we had in our machine learning 1 done something called ROC and AUC, right? So this is the ROC curve for classification error, right? If I see the AUC value, right? Again, class 8 mathematics, area under the area in a triangle will be half the area of the square if they're on the same base, right? So this one, just the AUC will be only 50% for this one, right? So this one is just 50% is the AUC, right? Now, if I draw the ROC for my other one, let's say the entropy, this is the ROC for entropy. You see that the ROC for entropy, right? And you see the ROC for classification error. The entropy value, if I look into the AUC value, area under the curve, right? Which basically helps determine that how good or how bad is my particular model is, right? So this AUC value is much higher for entropy compared to classification error. That's the reason why entropy is a better metric for doing the splitting as compared to the classification error. Right? What's the point? I think there was some question from someone. I think Sanyam had this question. So Sanyam, I think I answered your question, right? That why the classification error is unable to do, whereas entropy, because again it has more capability compared to classification error, it is improved. So, okay. So now let's come to something which is called the information gain, right? So again, this reduction in impurity, value, also the information gain helps determine that how effective an activity is in classifying the data, right? So again, this is what we are going to do. So yeah, quickly, there's another one which is called this Gini index. So Gini index is this red one, which you see. This is the AUC of the Gini index. So you see that Gini index and entropy, they almost share the same kind of a curvature, but still entropy is a better one compared to even the Gini index, right? So this Gini index, it comes from econometrics, right? So of all these three, classification error, cross entropy, Gini index, the best is the entropy, followed by Gini index, followed by this classification error, right? Okay. Now let's talk about the other problems. So decision tree tends to overfit. We have already said that, right? Decision tree tends to overfit. Now, whenever the decision tree are overfitting, right, then what happens is that you find that on the training data, you've got good performance, but on the validation, you get a bad performance, validation of the testing part, right? Which was, I think, the same question which Shifa was also asking, that how come we are measuring the performance based on the training data? Yes, on the training data, what you'll find is that decision tree will have 100% this thing, 100% accuracy. Why? Because again, we are taking all the records, right? I mean, we are considering the homogeneous tree, but that's not going to happen for a validation record. I think there is some question. Yeah, Shashwat has some question. Yeah, Shashwat, your question, please.
Sir, am I audible?
You're audible. Tell me.
Sir, recently, like yesterday itself, while studying for the IE, I read at most places that Gini is actually better than entropy computationally because the value ranges between 0 to 0.5 only, whereas in entropy it ranges up to 1.
So again, I mean, if someone said that the value is going only up to 0.5, mathematically it can be shown that there can be other values as well. But see, I mean, where Gini is better, in fact, the Gini index is the default implementation in Python and most of the other things also, most of the other packages. See,
right. So most Python users, like on GitHub and places where user reviews were there, so mostly Python users are mentioning Gini as the preferred choice.
Yeah, Gini is basically the default choice. I'll not say perfect choice; it is the default choice. Why? Because again, for the case of entropy, you have to do this logarithm calculation, right? So logarithm of very small fractions sometimes you have to make, and that at times gives some kind of a underrun, mathematical underrun problems, right? So for the part of the computational complexity only, entropy is sometimes not used, and that's the reason why Gini index is being used, right?
Okay, but then there is no such difference between the
there's
output.
difference. There's difference, as you can see. That in fact we are going to do a problem right now after this, where we'll solve the problem using all the three methods. So here you can clearly see that your Gini index is the one which lies in terms of performance, lies between entropy and the classification error. Obviously, Gini index is much better compared to classification error, but again a little poor when it comes to entropy.
Right? Okay.
So
right. Thank you.
Okay. So okay, so these are the strengths of decision tree: easy to interpret and implement, if then else logic, handle any kind of data, binary, ordinal, continuous, and no preprocessing or scaling required. Right? That's one of the advantages of a decision tree. So this is the Gini impurity index which we were talking about, right? So here Gini index, how you can also measure Gini index is via this. So 2 times proportion of observations in class 1 multiplied by proportion in class 2, or again, this is the one which I generally use. 1 minus proportion of the classes which is there, right? And 1 minus proportion of the classes, and squaring up those values, right? That is how you get Gini index. And let me show you a small problem. Just let me, this is a problem that we are going to solve, right? So here is some data, and the features or the attributes are the gender of a person, the car ownership, the travel cost, and the income level. 4 attributes. And then this is the target. There's some question. Let me check the question. Okay, so somebody is asking, kite is an algorithm wherein we are using chi-square to split, and we are not using any of this P to split. Is my understanding correct? See, all these algorithms like be it kite, be it entropy, be it Gini index, these are not basically algorithms. I'll say that these are basically variable selection measures, right? We use this to select my variables. That's what we use, right? Features for. Okay, but again, we'll do this problem, and I think all your questions will get solved. Okay, my first question to the class is that if I don't apply any model, right? Listen carefully. I don't apply any model, then what is going to be my prediction from this data set? I don't create any model. Based on the as is data set which you see on the screen, what is my prediction going to be? Shikha is saying bus. So Shikha, I am unmuting you. You have to explain that why it is bus. Yes, Shikha.
Sir, it's bus if we are not using any model based on whatever is given right now. That's the maximum number of people who have selected as their transportation mode, because the car 3 people have selected, train 3 people have selected, but bus has been selected by 4 people.
Exactly.
So
that's the answer. Thank you so much. So here, if we have not created any model, then bus is the majority, and our decision will be bus, right? Okay. But again, we are intelligent people, all of us in this particular session. We are intelligent and will probably become more intelligent if we apply this methods from decision tree. So let's see how we can do that. Okay. So this is the, so if you see here, 4, 3, 3. So 10 records. 10 records we are having, right? And the proportion, if I see, 40% is bus, 30% is car, and 30% is train. That is the proportion which I'm seeing, right? So bus probability is 0.4, car is 0.3, and train is 0.3. Let's do one thing. Let's find out the impurity using these values. So if you remember, for classification error, that would be 1 minus maximum of the proportions 0.4, 0.3, 0.3, which is basically 1 minus 0.4, 0.4, this is equal to 0.6. That is my classification error value for the root node. For the entropy, this is going to be minus 0.4 log to the base 2, 0.4 plus 0.3 log to the base 2, 0.3 plus 0.3 log to the base 2, 0.3. That's my entropy. And Gini will be 1 minus 0.4 square plus 0.3 square plus 0.3 square. So Sanyam, you see that how easy it is to calculate a Gini index, right, compared to entropy, right? Classification error is probably the easiest to calculate, but again, it's not that accurate, so we are not going to use that, right? Okay. So again, these are the values. Classification error, entropy 1.571, and G index is coming as 0.66. So again, I think someone in the class said, I don't remember, Tanyam or someone else, that Gini index lies between 0 to 0.5. So already you see that it is already valid, right? We are getting a Gini index of 0.66, right? It's not that it lies between 0 to or 0.5, right? If it is mentioned somewhere, maybe that was with respect to some context where it is mentioned, right? Okay. So let's do one thing. Let's split based on the travel cost, right? So I have this travel cost as cheap, expensive, and standard, right? If you go back to the data, so I had this gender as a feature, car ownership as a feature, travel cost as a feature, income level as a feature. Let's first split it based on the travel cost, right? Why travel cost? Again, there's no reason. I've just selected travel cost, right? You could have selected any other one, but again, I would just like to illustrate. So travel cost cheap, right? So 5 records are there, of which 4 are saying bus and 1 is saying train. 4 bus and 1 train, right? If I take travel cost as expensive, all the 3 are saying car. If the travel cost is standard, all the 2 are saying train, right? So as you can see that for the travel cost expensive and the travel cost standard, my target or my decision has already become homogeneous, right? So I don't have to take any further decision on this. So travel cost expensive, answer is car. Travel cost standard, answer is train. No problems with that. Travel cost cheap, there is some problem, right? Because again, it is not homogeneous. It is split between these 2 classes of bus and train. So let's say if I stop my decision tree here, right? So this is the decision tree which I have created. I have split based on the travel cost. And let's see if I stop it here, what is the accuracy of this particular decision tree? Accuracy of this particular tree. Who is going to give me the answer? Accuracy. Come on, I think we have discussed this particular point. At least 1 or 2 people can give me the answer, right? If one answer has come through, Shikha is saying accuracy is 4 by 10. Shikha, that's not the correct answer. Sambit is saying 10 by 11. Sambit, just again redo it. Anas is saying 8 by 10. Again, not the correct answer. Come on, guys. Hari is saying 9 by 10, and that's the correct answer. 9 by 10. How? Let me show. So here, 3 of the 3 records will be correctly classified, right? Car, and it is homogeneous. Pradeep has saying 9 out of 10, and that's the correct answer. Here, 2 of 2 records have been correctly classified. All will say train. But here, if I see there are 5 records, of which 4 are bus and 1 is train. If I have to go by the majority, so 4 of the 5 I'll probably have correctly classified, right? So I had 10 records, of which 4 plus 3 is 7 plus 2, 9. I have correctly classified, only 1 misclassification. So 9 by 10 or 90% is the accuracy of this particular tree, right? Otherwise, you could have also done the calculation in this way, that I have 10 records. So 5 by 10 into this one is 80%, plus 3 by 10 into 100%, plus 2 by 10 into 100%. So basically 5 by 10 into 80% plus 5 by 10 into 100%, right? So half of 80% and half of 100%. So this is 40 plus 50, 90% is the answer, right? Okay. Now you see what has happened because this is homogeneous. If you calculate the this thing, impurity is 0 by any of the means. You use entropy, Gini index, classification error, the impurity is 0. Here also, impurity values there is 0. 0 impurity values. See out here, impurity value. So I'll not do all of them. Let me do the classification error, right? So classification error will be 1 minus maximum of 4 by 5, comma 1 by 5, which is 1 minus 4 by 5, which is 1 by 5 equal to 0.20, which is the value which we get out here. For the case of this Gini index, it will be 1 minus 0.8 squared plus 0.2 squared, whatever value comes up, it comes as 0.320. And the entropy value will come out as 4 by 5 log to the base 2 4 by 5 plus 1 by 5 log to the base 2 1 by 5. I take a negative in front of it. That will give you the entropy value, right? Okay. The next thing we need to find out is the reduction in impurity or the information gain. So impurity at the parent table minus the impurity values at the child table. That's the next thing that we are going to find out, right? Okay, Shukanto is having a question. Yes, Shukanto, let me unmute you. Yes, Shukanto.
Yes, sir. Regarding the Gini index, considering that as a performance metric, 0 indicates the purest class, like it's 100% homogeneous, right?
Yes, yes.
Pass through the question. One is that whenever I'm reaching a Gini index of 0 means that I won't split further into further nodes.
It doesn't. So it is true for any of the metric. If you get a configuration where the impurity value is coming out as 0, so be it coming from entropy or Gini index or from classification error, which means that you have reached homogeneity. You can see out here in both the cases, right? Travel cost standard and travel cost expensive. It's all 0.
Actually, my question was concerning only Gini index, or let's say even any of the other metrics.
Right.
It could be that, I mean, my target would be to reach 0, but it could be that I always don't reach a perfect 0, right? So anything which is very close to, which is like as good as 0 in mathematical terms, is that also acceptable? And the second part being, if I stop splitting there, even if I don't get a 0, but a number as good as 0, but then is there an equivalent of a cost function, like where I can reduce the, improve my performance metric to say that I iterate my model again and I get a number which is closer to 0, if I'm making sense.
Anyway, so again, if I would have understood your question correctly, that is, you would like to know something to do with the stopping criteria. When should you stop? Is that your question?
Sorry, sir?
Is the question is that when we should stop, at what particular impurity value you should
Yeah,
stop?
I mean, does it always have to be 0, or like, because in certain circumstances, I may not be reaching 0, but a number which is, let's say, very close to 0. So do I stop there, or like I split further?
I think in most of the cases, you should be able to reach the 0 value. In most of the cases, right?
Okay.
Not all cases, not all cases.
Yeah.
So, I mean, whenever you reach a 0 value, which means what? That you have completely got homogeneity. Now, there will be some, sometimes based on the data which is there, which might inhibit you from reaching 0, right? It is basically a problem with the data set, which might inhibit from you from reaching 0. But otherwise, if you are looking at the principle in which decision tree works, the principle is that I should go to a state which is more pure compared to the previous one, right? In some way or the other, that will lead you to a 0 state, right? But again, having said this, it's not that how close to 0 you should get your model to. It is more to do with the performance metric, right? So let's say here at this point in time, you have already seen that I've got a 90% accuracy. And if I'm
Okay.
saying that, okay, my target is 85% accuracy, I've already got 90%, so I can stop out here. But let's say your target was not 90%, but let's say your target was 95%. Then I'm still far from that particular metric. I probably need to split further before I attain a 95% accuracy.
Okay, so here I focus more on accuracy, let's say compared to linear regression, where my focus would also be as much as on the error metric, right? If I've
No,
I've
so
understood.
here the accuracy which I'm talking about, that is the error metric.
Okay,
Here the accuracy is my error metric, right? So here, so when I'm saying 90% accurate, which means error is 10%. So
okay,
let's
so
say your
huh.
error target is 5% or less. If that's the case, then probably you have to split it further. If your error target was, let's say, that 15% or less, already you have reached that. You don't need to split further.
So the evaluation of a decision tree is its accuracy, not the measures in impurity.
The again, it's not for decision tree, it's for every machine learning model, right? The metric which we have already studied in ML1, right? So some or the other of this metric will be used for evaluating it. And all this impurity value or this homogeneity, these are means to reach those performance metrics. These are means to reach it. It's not that you have to reach this one, right? These are means which will ensure that you reach the performance metric.
I see. Okay.
Right?
Yeah.
Okay.
Thank you.
Sambit is having a question. Yeah. Yeah, Sambit.
So, Professor, here means here what work this entropy, Gini index, and classification error is doing. The same thing we have learned in chi-square test also, right? There also it is doing the same thing. Means it is finding out to which will be the best option to split the branch, right?
Yes. That's the objective. That's my objective. That which branch will I use to split, so that at the end of the day I get a better or a homogeneous kind of thing. That is the objective. Exactly.
Okay, so as we know in Python, it is like basically this Gini index is the default one. Okay,
yes.
So this chi-square only is being used in this CAID algorithm, or we can use in different algorithms also.
See this this chi-square. It's basically, as I said, it's a measurement which can help you detect that which variables are important, right? And this chi-square test, when used in KITE for doing a decision tree, that's a KITE algorithm, right? So again, I mean, there are, see, whenever you are using in Python, right, you can use any one of the configurations. Say, for example, the default is Gini index. You can also use the entropy as the mechanism to do the splitting, right? It all depends on, okay, which particular algorithm you want to use, that is one, and then how you'd like to explain this algorithm, right? Based on that, you select. But again, it has been seen that entropy by far is the best metric which is there, right? When it comes from the data scientist point of view, statisticians, by the way, they will prefer KITE more compared to any one of the other methods, because again, KITE has its root in chi-square test, which is a classical method in statistics.
Yeah. Okay.
Fine.
Thanks.
Okay. Shikha has a question. Okay. Yeah, Shikha. Yeah, Shikha.
Yes, sir.
Yeah.
Thank you, sir. Sir, actually, I have three questions. The
Three
first
questions. Okay,
question is
good.
about calculation of Gini index, right? So I guess the value comes to be the same, but at least in our async content, I think the way it is calculated is slightly different, where they are multiplying, where they are adding the products of probability of a class and 1 minus probability of the class. So like here, it's point. So yeah, just here, just I can tell you here.
See, all this three are the same. I think
Okay.
this is how it has been done to be async.
Yeah.
So
One minus.
This basically evaluates to this, and then finally this. It's all the same.
Okay. Okay. Yeah, it must be a derivative of. This must be a derivative of what? Yeah, here it is 2 into. Oh, because of the classes you're saying. Why is this 2? So second where you're saying 2 into, so it is sigma P C. Yeah,
So
sorry.
here it is 2 classes they have taken, right?
Yeah.
So the first case is the product of the classes. In the second case, it is the product of the class and the complement of that, right? So let's say
Correct.
you have 2 cases, let's say 6 in one and 4 in the other.
Right.
So here this one is saying 2 into let's say 6. This is probably 0.6 into 0.4
4. Yeah.
plus, once again, when you go to the next class,
Yeah. Yeah. Same thing.
0.4
Into
into
0.6.
0.
Yeah. Yeah. So
Like
there
that.
is no 2 there. Actually, there is
But
no 2 there. So because it is already.
I think they're referring to this one. This first one is what?
No, sir. No, sir. I'm referring to the second one. At least in the async, the way it is written, it's written just sigma. There is no 2. There is
Okay.
sigma of whatever you've calculated here. Probability of a class 1 and 1 minus probability of class. So I don't.
Sorry, my bad. My bad.
Yeah, this is not 2.
No, my bad. Right. I'll tell you why. So this part is fine. This part is fine. This part is fine. So this is valid only for 2 classes. So for 2 classes, what you see is that this thing and this thing is the same. So basically, this is equal to 2 into 0.
Correct. But then there shouldn't be any sigma, right?
Which one?
There shouldn't be.
There should not be any sigma. I think what you're saying is correct.
Right. There shouldn't be any sigma. Okay. This is my
part.
first question. Second question is, if you would just go back to the error where we were looking at all the 3 errors in the current example that we are studying.
Yes.
Further next slide. Yeah. This one. So here, sir, if you see in the first instance, there is only 1 error, right? 1 out of 5, where the split is happening, and then 4 are bus and 1 is stream, and by majority there is only 1 error, correct? One instance that is incorrectly classified. So we just saw that Gini index and entropy are actually very close, the way we calculate. But here, when you're calculating it, Gini index seems to be more closer to classification error than entropy. Like there's a huge difference between Gini index and entropy. So I guess huge difference in the sense the way we are interpreting it, right? So Gini,
the way they're interpreting exactly.
It's a complement of so one is entropy and one is, so Gini impurity, the maximum value is 0.5. So it's 0.3, and then entropy maximum value is 1, correct?
So for all the cases, the maximum value is 1, and the minimum value is 0. Right?
But for Gini index, I think if there are 2 classes like their bus and train, the maximum that, at least that's how the async is telling us, the maximum that one Gini impurity can reach is 0.5.
Yes. So in the case of 2 classes, binary classes, yes, the maximum that it can reach is 0.5. But here you see that since I have 3 classes, my Gini index was more than
0.66. Correct. Right. Now the question, so my question is first, okay. So you're saying 0.722 and 0.3 is sort of equivalent in that sense, or very close.
See, whenever you are using this metric, please don't mix and match those metrics.
Okay.
If you're solving something in entropy, keep entropy as the metric 12.
Right. No. Right. So here the question main is, so there we should actually need to calculate the original entropy and Gini index and classification error for the original data set to be able to interpret this, right?
Yes.
Whether there is an increase or decrease, correct?
Yes, exactly. So that's the next thing which we'll do right now.
Okay. And the increase or decrease, is there absolute values, or do you, the way you've calculated, like it is 1 minus, like you calculated a decrease in entropy at some point of time, and that was like 1 minus, and it was more complex than just looking at the values. My understanding was,
let's do it.
Let's look at it. Okay. All right. Thank you.
Yeah. Anyone, any other question before we move ahead? Anyone, any other question? Okay. So let's proceed. Right. This is the part which is not there in most of the books also as to how it is done. Right. But yeah, it's important that you know it. Right. Okay. So this is what we are going to do right now. Impurity value at the root minus the impurity value at the child node. So this is what I get the gain value, right? Entropy, Gini index, classification error. How we are getting this? Let me show that to you, right? Okay, so let's come here. So here, if you remember, classification is 0.6, 1.571. So classification error is 0.6, Gini index 0.66, and entropy is 1.571, right? Now reduction, if I look into classification error is 0.6. So I had 10 records. So 10 by 10 into 0.6 was the root node, minus here 1, 2, 3, 4, 5, only 5 records I have. So 5 of 10 into the value was 0.2. Plus this one is 0, this one is also 0, 0. So 5 by 10 is half, half into 0.2 is 0.1, and here 10 by 10 is 1. So 1 into 0.6 is 0.6. So 0.6 minus 0.1, this is equal to 0.5. And that's the value which we have in the next slide. For the case of Gini index 0.320, at my root node it was 0.66. Right? So let me rub this down. So the root node, it was 10 of the 10 records giving 0.66 minus 5 of the 10 giving 0.320, and then rest as 0, right? So this is 0.66 minus half of 3.320, which is 0.160. So this is 0.50, which is basically the value that we will get out of it. So this is what I get by Gini index, classification error, and this is what I get via the entropy. Okay, so that's one part of the piece. Now what? What's next? What's next? How do I proceed? This is just one of the part. How do I proceed? Yeah, anyone? How do I proceed? Is my job done? Is my job done? Or there is something more remaining? Is my job done? Somebody is saying no. So what is remaining? What is remaining? Shika is saying calculate accuracy. No, Shika, no. Is my task completed? Is my question to you. Sanyam is saying no. Fine. I mean, do it again. Say why it is no. Sanyam is saying optimization. Again, what do you mean by that? Simple. What's my next step? What's my next step? Information gain. So Hari is saying information gain. So information gain is, this is the information gain. Gain. I've already calculated. Somebody is saying optimize the model. Can I get a very simple answer? Tuning. You can get lot of jargons are coming in, right? Shikha is saying split further. Okay. Decision tree finalization is what Shashwat is saying. I'm still not getting the right answer. Still not getting the right answer. Still not getting the right answer. See, why none of you are asking that, professor, why should I split on the travel cost? What made you split by the travel cost? What happened to the other features? None asked that. That's what we are going to do right now. The same thing that we have done for the travel cost. The same thing we are going to do for all the others. Right? So here is where I have split based on the gender. So gender female, gender male, and this is what I see. Here is where I have split based on the car ownership 0, 1, and 2. So in this particular case, it is homogeneous. And then income level, high, low, and medium. So high is homogeneous car, low is homogeneous bus, medium is not homogeneous because there is bus, car, train, all the cases. And for each of the cases, what I need to also do is I need to calculate the information gain. Right? Again, I think already we have done one of the cases, right? Let's not do each and every one. It's the same calculation. But then after this calculation is done, the next part is comparison, right? Comparison of the information gain which I got. So now my question to you is that which one do you think is the variable on which I'm going to make the split? Which one is the variable on which I'm going to make the split? This information gain is nothing but the reduction in impurity. So which one is the variable on which I'm going to make the split? So Shikha, Hari, anyone else? Anyone else? Shikha has given the answer. Hari has given the answer. Anyone else? Shashwat is saying gender. Shukantu is saying gender. Sambit is saying lowest one. Okay. Anyone else? So Shikha and Hari, they have given the correct answer. The answer is travel cost. Why travel cost? Because again, this values, information gain, is basically the amount of reduction in impurity that you have achieved. Right? It's not the impurity, but the reduction in impurity. Right? Impurity value, lower, better it is. Reduction in impurity, the higher, the better it is. So here, if you see, if I use entropy, across all these values, this is the lowest. If I use Gini index, across all these values, lowest. If I use classification error, once again across all the value, lowest. See, by the way, you don't need to use all these three. You can use anyone. You can use either entropy or Gini index or classification. Anyone. You don't need to use all the three. But again, you need to do this comparison. And the comparison part, I've seen that the maximum reduction is happening for the travel cost part, and that's why we are using travel cost as our variable. Sanyam has a question, so let me allow him to talk. Yeah, Sanyam.
Professor, am I audible?
You're audible. Tell me.
So, Professor, like in this matrix, what we are depicting is information gain are the values for these particular matrices.
Yes, information gain for these features, not the matrix, for these features.
Okay.
Ah.
Okay,
No,
then it's fine because I was thinking like these are the value for the Gini index and
no,
entropy. That's why we have selected it.
So the Gini index and the entropy already we have done out here.
Okay.
So on that aspect, yeah. See, there's so many values of Gini index and the entropy, right? We need to find out some way in which to combine them, right? In the information gain part, that is where we had done the combination part, right? Taken the impurity at the root node, root minus weighted average of the child nodes, right? This value is giving me all these things, right? Okay. So now travel cost becomes my first splitting part, right? So once I have split based on the travel cost, so this is how it looks like, right? As I said earlier, this one homogeneous, no need to split further. Homogeneous, no need to split further. This one not homogeneous, I need to split further, right? So here, because these have become homogeneous, I don't need to take even this particular parts. Let me just concentrate on these 5 records, right? So this, let me come to the second iteration. So this is how my data looks like. Gender is female, car ownership 0 and 1. Travel cost, all are cheap. So again, travel cost, not needed, no need to take. Income level, low, medium, transport mode. This is how it is. So travel cost is not required. So these are the 3 features on which I need to do this project right now. Gender, car ownership, and the income level. Right? Once again, I'll do the same thing which we have done earlier. Right? So this is, so right now, this is my parent node. Right now, this is my parent node, which is having 1, 2, 3, 4, 5 records. 5 values are what is having my parent node, right? Entropy, Gini index, classification. These are the values which I'm getting for the parent node, whatever was the earlier calculated. Once again, what I'll do is I'll split on the gender, on the ownership, and on the income level. And then probably I'll take a call. But again, before even I go to the next part, can anyone tell me that which one will come as the most important variable? What do you think? What do you think? Which variable will come as most important in this particular part? Which variable is coming as most important? People have answered. So Hari has given the answer. Shika has given the answer. Okay. Some other people, if I can get the answer. If I can get, it's all there. It's all there in the screen. It's all there in the screen. You just have to do the comparison. It's all there in the screen. It's all there. Yeah. Anyone? Shika and Hari has already given the answer, and the correct answer has received. But yeah. Anyone else? Okay. See, the answer is gender. Why? Because again, if you see the gain, it is maximum, right? For entropy also, this maximum, in index maximum. Classification error, by the way, you see that classification, that's why I said classification error is not the best metric. See, it is unable to classify further. It has stopped spreading, right? Classification error. It's all coming out as 0. But yeah, even if you use entropy or even if you use Gini index, both the cases, we are finding that gender is coming out as maximum. So this is how it is coming. So for gender male, already it has become homogeneous. All of it is saying bus. While for the gender female, still there are ambiguity. Right? So for the gender male, I have already got homogeneity. Right? So people with a income, this thing, income, medium income, but having a gender male, they will prefer bus. People with a medium income, right, having this thing, gender female, still there's some problem. So this is how my decision tree looks like at this point in time. So travel cost expensive, it will always be car. Travel cost standard, it's always going to be train. Travel cost cheap, I'm sorry, not, it was not standard, cheap, my bad. Then if the gender is male, then goes via the bus. Gender is female, still need to split further, right? Still need to split further. And again, if I do the third iteration, again, you can see I can take any one of this, right? Ownership 0, 1, or income level low, medium. Any of the two I can take, and this is my final tree, which looks like. So now how to derive the rule? The rule is very simple. If travel cost is expensive, then go via car. If travel cost is standard, go via train. If travel cost is cheap and gender is male, then bus. If travel cost is cheap and gender is female, then if there is no car ownership, then takes bus. If this particular person has a car ownership, takes train. This is the final decision that you got into. My question to the class is, do you see any problem with this particular tree? Any particular problem with this particular tree? You think there's some problem in this particular tree? If yes, what exactly is the problem? Any issues which you might get in the tree? Any issues? Any issues which you might get in the tree? Anyone? Any issues which we might get in the tree? Shika and Sanyam has given the answer. It's one data point in the terminal node, just one data point in the terminal node, right? So here only one So here, I think you had two records. Here you had, sorry. Here you had three records. Here you had three records. Travel cost cheap. I think how many records you had? I think look into it. I think cheap had about 5 records. 5 records are having. For the male part, 3 records have come in. 2 records you had. One record out here. One record out here. Right. So basically, you have created a overfit tree, and that's a problem. That's a problem. Right. So whenever you're creating an overfit model, it's not a model, because what is happening is that the tree is basically memorizing all these values. It's memorizing all these values, right? So that's a big problem with decision tree, because by principle, because the decision tree, it would like to give you some kind of a homogeneous configuration, right? It might end up in things like this, right? But again, we'll come to how we can do the other part. But again, these are the populative decision tree, no domain knowledge required, classification is based on probability alone, and can handle multidimensional data, right? Issues with the decision tree is handling continuous attribute as a feature. What happens if you're having a continuous attribute as a feature? What happens is there might be multiple splits in the classes. So let's say that I take the people in the class in this particular session, and let's say these people, they are having age between 18 to 48, right? If it was already defined in some particular classes, it's easier. If it's not there, then probably one of my splits can be between people between 18 to 22, and then 22 to, let's say, 28, and then 28 to 38, and then 38 to 48, like this. Or some other split can be 18 to 32, 32 to 42, and 42 to 48. Now, this particular part, because it's a continuous variable, where to split, that sometimes becomes challenging, and you have to do a lot of optimization on that particular part, right? Choosing an appropriate attribute selection measure, right? Should you use entropy or Gini or Tide, right? You can't say beforehand that which one will give better, but again, by default, entropy basically gives you some kind of an edge over the others. Handling training data with missing attribute value, right? This is a problem in most of the cases. So here also, training data with missing attribute value is a problem. Handling attribute with different cost, this will not talk about right now. And improving the computational efficiency. So many computation has to happen, right? It's a greedy method. So many computations are happening. Improving the computational efficiency is also challenging, right? So these are some of the issues in the decision tree, right? So that's why I said categorical values, only 4 possible values. Continuous 0 to 100, infinite number of possible values for splitting, right? Okay. I'll move to the regression tree, but I'm just wondering, can we take a small break? Right? Can we take a small break? What do you think? Let's come back at 9:05. What do you think? Say, it's 8:57 in my clock. Let's come back at 9:05. Yeah. Okay. So thanks everyone. Let's come back at 9:05 and continue the class. This is the regression tree is what we'll do. Small part remaining, right? And that will be the end of a decision tree, end-to-end complete tree. After this, open up any book. I think you'll be at peace. No problem. Right? Okay. So again, I'm muting myself and turning the camera off. We'll come back and do the regression tree sort. 9:05. You can write it on the screen. Please come back. Okay, so let's start coming back. I hope this particular break was useful for you, right? Okay, so let's now move it to something called as a regression tree, right? And till this time, we were doing the classification tree part, where we're trying to classify some particular values. And now we'll do the regression tree, where the objective would be to find out some continuous values. Right? By the way, one thing is there is that be it classification tree, be it regression tree, the way in which we measure, I mean, we build the tree step by step, iteratively, that process doesn't change much, right? Irrespective of the decision tree that you're using, classification or regression, it remains the same, right? So here, regression tree, as you can understand, when the target variable is continuous, that is when we use the regression tree. And reducing the variance of the target is the key method in which we use the regression tree. Now, why the variance part? See, here for the regression tree, our target is continuous or some kind of a numbers, numerical numbers, right? Now, for continuous targets, for numerical numbers, the lesser the amount of randomness in the numbers, the better it is. If all my target variable, the numbers, they are the same number, which means the variance will be zero, standard deviation of the variance will be zero, which means that there is no disturbance in the values. It's all homogeneous. Whereas if the values are spread wide apart, that is when there is some issues out there, right? So with that, let's take the same problem, but this time we have the number of golf players on the field, right? Same data which we have done. This is my target. This is my target variable. Same data set. Right? Now, how we can solve it using the regression tree? Right? Like we have done earlier, we'll do the same thing. Let's first look into the outlook. So outlook, we have three values: sunny, overcast, and rain. Right? So first is at my root node, assuming that there are no other things, let's find out the impurity. So here impurity is nothing but the variance, or even you can also use standard deviation, right? As long as the interpretation is the same, it's fine, right? So either use the variance or the standard deviation and find out the amount of impurity, right? Variance or standard deviation, find out the amount of impurity. And here the amount of impurity which comes up here is this. This is the number of golf players on the field. This is the average number of golf players, 39.78. And then I find out the standard deviation, which comes as 9.32. So at the root node, I get my standard deviation or the variance. As I said, you can use either of it. Right? Standard deviation is nothing but the root over the variance part. Right? Either of the two you can use. So let's look at the outlook. Outlook can be sunny, overcast, and rain. And let's calculate the standard deviation for the outlook. Right? So this is the outlook sunny. 5 values are there. For sunny outlook, the standard deviation is coming out as 7.78. Outlook overcast. So sunny had 5 records. Overcast had 4 records. Right? This is the average value. And this is the standard deviation, 3.49 to the standard deviation for overcast, right? See, pretty small value, right? Remember, in the previous also, the overcast is the one which was giving us a better homogeneity, right? Okay, and let's look for the rainy outlook. So outlook is rain. It's coming as 10.87, pretty high, pretty high. The next thing that we are going to do is we are going to find out the pooled standard deviation or the pooled variance, right? So 4 instances of overcast record, 5 instances of rain, 5 instances of sunny, right? So 4 by 14 into 3.49 is for overcast, 5 by 14 into 10.87 for the this thing for the rain, and 5 by 14 into 7.78 for the sunny. Overall impurity comes out, weighted impurity value comes out, or weighted standard deviation comes out as 7.66. So if I use outlook reduction, 1.66 is what I get, the reduction of the value. What next? Is my problem solved? Is my problem solved? If yes, why? If no, why not? Is the problem solved? Yes, no, maybe. So, Shika is saying no, but again, why? Next question is why? Can't just say, problem is solved or problem is not solved. You have to come with the logic, reason why the problem is not solved. We need to compare with the other features. Exactly, and that's what we are going to do. Exactly. So this is for the temperature, right? So this is the temperature hot, for instance, cool, for instance, mild, 6 instance. So 4 by 14, 4 by 14, 6 by 14 into this value, 3.95 into 5.7.65, 8.84 is what I'm getting. This is a reduction for the temperature part. Same I'll do for humidity, 0.27, and for wind, 0.29. Right? Once it happens, we have to do the comparison of the reduction in the impurity here, reduction in the standard deviation, or if you have used variance, reduction in the variance part. So which one to take? Which one to take? Which one to take as my most important variable? Which one to take? Which one to take? Which one to take? Shika has given answer. Sambit has given answer. Rashput has given answer. Which one to take? Some more answers I'll expect, and then I will move ahead. Shika, Sambit, and Shashput has already given the answer. Yeah, anyone? Anyone else? The answers which people have given are humidity and outlook, right? The answers which people have given are humidity and outlook. And by the way, the correct answer is outlook. I think whoever said humidity, see, I'm looking at the reduction part, right? So how much I have reduced? The more I have reduced the impurity, the more I have reduced the standard deviation, better it is, right? See, for a particular node, see, this is a part where many people get confused. For a particular node, when I'm calculating the impurity, the lower it is, the better it is. But when I'm considering the reduction in impurity between the parent and the child, the reduction has to be maximum, right? The reduction, if you have a maximum reduction, then means that the impurity value has been reduced to the maximum possible extent. So here, outlook is the one. As you can see, it has given the maximum reduction in impurity value. That is what I'm going to select, right? Okay, so this is how it looks like right now. So outlook overcast, outlook sunny, outlook rain. Right? So now what I'm going to do is, once again, I'm going to split it on the sunny outlook, right? So sunny outlook, earlier it was 7.78. After doing the splitting based on the temperature, right? And the other variables, this is what I get. Temperature 4.18, humidity, wind. Which one to use right now? Which one to use right now for the reduction? Which variable? Temperature, right? Exactly, temperature. Maximum reduction it is giving. So let's split based on the temperature. So outlook sunny, temperature hot, mild, cool. This is how it looks like. See the problem. One record, two records, only one record, two records. Big issue, right? So that is where the pre-pruning part will come in, right? So basically, if you're having less than 5 rows of data, you should take a note on that, right? Less than 5 rows of data, not a very good indicator for splitting. Standard deviation, less than 5% of the initial standard deviation, right? That's probably also where you can stop, right? So because if you don't prune it further, what will happen is that it will result in some kind of a overfitting. Right? So less than 5 rows of data or standard deviation less than 5% initial standard deviation, all those things. That is when the tree looks. So this is how the tree looks like. Outlook overcast 46.3, that is the average value. Outlook rain is split based on the same thing which we have done earlier. Wind 47.7, strong is 26.6. Sunny temperature, cool is 38, hot is 27, mild is 41. Right? This is how the final decision tree looks like. But again, you should ensure that there are not too fewer records at the child node or the leaf nodes. Otherwise, it's going to give me a problem for the overfitting. Right? Okay. So let's come to the last few pieces of this overfitting and underfitting. So what exactly is the overfitting and what exactly is the underfitting? Right. So overfitting occurs when the machine learning algorithm captures the noise of the data, too much noise of the data, and underfitting occurs when the machine learning algorithm cannot capture the underlying trend of the data. There's an underlying trend in the data which is there, and the machine learning algorithm is unable to capture that. Right? That is the underfitting part. Like again, if I give you some real examples, right? Maybe the real life example is just the opposite of this. So let's say that you have gone to a tailor, right? You've gone to a tailor, and this tailor has created a dress, right? It has created a dress which probably you can wear, right? Your brother can wear, your sister can wear, your parents can wear, and again, if you have child, your children they can also wear. It's so loose, it can take into account anyone and everyone, right? We generally say that this is the overfit part, right? You have created an overfitted kind of dress. See, for someone it can be overfit, for someone it can be tight also. But again, so generally you would say that okay, this is something which it's unable to capture the underlying. So the dress was created for you, right? The dress was created for you. But again, right now, it can capture everyone, right? So again, in your parlance, it will talk that this is an overfit case. In the terminology of machine learning, it will probably be an underfitting case. Why underfitting? Because again, it is unable to capture the underlying trend of the data. In your case, your body, it has some different contours and everything. So unable to capture that. Right? It's unable to capture that. That's the underfitting case. For the overfitting case, what happens is the machine learning captures even the noise of the data. If on the other hand side, the tailor has created a dress, right, which perfectly fits your body, right, right from the wrist to the arm, right, to the waist, everywhere it is a very perfect fit, right? Even if you lose a little amount of weight, you'll not fit into the particular dress. Even if you gain some particular weight, you'll not be able to fit into the particular dress. Right? So that's also not desired, right? Whenever we create, like we buy our dresses, right? Either we go from the factory fitted dresses, which really creates a standard size for many people, or even if we buy it from the tailor, like custom build it from tailor, we ensure that okay, at least it takes the sizes properly, not like something where is capturing too much of the noise in the body, right? So that is the overfit and the underfit, right? Underfitting is when you have not been able to build a good model, and overfitting is where you have not built a model, but again you have memorized the values, right? In the case of this machine learning part, right, the overfitting case is where what you have done is that you have just memorized all the records without creating any model. And underfitting is when you have probably created a very simplistic kind of assumptions. Say, for example, in the data that we had about people playing golf or not playing golf. So here, let's say we have made some assumption or some hypothesis that okay, if it rains, people will not go out and play. So rain, play, rain, don't go play. No rain, go out and play. Right. So here you are assuming. So it's a very simple assumption that okay, rain, people don't play, so people should not go out. No rain, people can always play. So that's the case. But then again, when you look into the data, there might be so many other factors apart from rain which influences whether someone will go out and play or not. But the very fact that you have made some simplistic assumption, it basically prevents this whole thing from getting to a good model, right? So that will be an underfit model. Overfit, as I said, that if the model is building like this, that okay, if it does not rain, and if the temperature, let's say, is less than is between 38 and 40, and if the wind is in this particular direction, and if the humidity is like low, medium, or high, then only go out and play. Otherwise, don't play. Right? It becomes too sophisticated a part, right? Because these are the only features which are given. So whenever you're getting some fresh set of data, if it exactly matches with this parameter, then only the prediction will be possible. Otherwise, the prediction will not be possible. This is also bad. This is also bad, isn't it? So this is the case of the overfitting, right? You have made too many assumptions. Right? And underfitting is when the assumptions are too much simplistic, and those simplistic assumptions doesn't actually convey the underlying motion of the data. Right? Okay, so after avoiding the overfitting part, how you can avoid? See, by default, as I said, that decision tree, the objective of a decision tree is to enter a region of homogeneity. Right? It will grow till a point that it has become homogeneous. Right? So that's the bad part. That's the bad part. Right? Why bad part? Again, that's the objective. But because of some underlying issues with the data, it might give rise to cases where each and every leaf node will have only one record. Not good. Right? It's not good. So what you can do is you can fully grow the tree first. A fully grown tree, you'll find that it will be having a 100% accuracy or any other performance metric that we use. And then probably you post-prune it. You post-prune it. What is post-pruning? After the tree has been built, right? Then probably you prune it till a particular level where you find that, okay, I mean, one is I have built a generalized model, and the other part is that I have reached some kind of a performance metric which is there. So a fully grown tree will have a 100% accuracy. Let's say you're someone who needs not 100%, only 90% is fine. So you'll probably prune it to a point where it gets just more than 90%, and then you should be fine with that. Right? So that is one way of this avoiding the overfitting part. Also, there are something called as hyperparameters, right, which will also help you right? Stop the growing of the tree, right? Okay. So what I can do is that, let's say I can say that, okay, come what may, I don't want a tree which is beyond a depth of 3, right? It will go only up to depth of 3 and not beyond that. Right? So that is when I am doing a pre-pruning. The previous one was post-pruning, where I have fully grown the tree and then I have pruned it. Other is pre-pruning. I've just said that, okay, at this particular point, at this particular depth is where the tree should be. It should not give any further on this part, right? That's the pre-pruning part. Also, when we said that some kind of a performance metric has been reached, right? I showed you, right, at every point at what performance metric is free. Right? So there also, if you have figured out that, okay, this is the particular performance metric which I would like to be. So performance metric part can be used both for pre-pruning as well as for post. Right? If you do a post-pruning, you attain a level of 100%, and then you prune it to a point where you know that, okay, this is the performance metric at which I would like to find yourself. For the pre-pruning case, the other way around, that, okay, you measure the performance at each and every point till your desired performance level has been reached, right? Okay, the other thing which missed out somewhere is things to do with something called let me just check quickly. I think I've shared that with you, but just check. Yes. Okay, so again, overfitting, underfitting, we were already talking about this, right? Decision tree generation, right? This is how we generate the decision tree. You have the data, right? Full data, right? And then you split the data on training versus this testing. This training part, what you do is that you basically select the best attribute, right? Information gain, gene index, gain ratio, right? Break the data into smaller and smaller subset till you have created that. And once the tree has been created, test data goes into evaluate the model, right? And this performance evaluation measures, whichever giving you a good one, there you are stopping the tree. Now for growing the tree, right? As I said that you post prune the tree, right? Or again, you stop the growing of the tree at a certain level, or you go from a tree to a forest, right? What is a forest? A forest is nothing but a collection of many small decision trees, a collection of many small decision trees. These are some of the methods we use for overfitting, right? To stop overfitting. Forest comes under the purview of ensemble method. Right? So again, in the next week's class, we are going to talk about this forest and the other method. But coming to some of the hyperparameters which decision trees having. So one is the split criteria, entropy, Gini, chi, those are some of the methods which can help you determine that on what basis to do the splitting. You can use the maximum depth, right? That's also something that you can use to determine that when to stop doing the decision tree, right? There's also something called as a minimum sample split. Minimum number of samples needed in order to split a node. So let's say that you have come to a configuration where your decision tree at a particular node is having, let's say, 12 records. So let's say that the minimum sample split at the decision tree is 10. So 10 is less than 12. So yes, you should be able to do the split. Right? So after the splitting, maybe it becomes something like a 8 and a 4, which is fine. Right? So now that has become 8, or it has become 4. So 8 is less than 10, right? 8 is less than 10. So earlier you had 12, which was greater than 10. But now you have 8, which is less than 10. So you can't split further. So you'll stop it here only. This is 8, this is 4. Right? You are unable to split it further based on the minimum sample split. Come to the other one, which is the minimum sample leaf. Right? This is very close to the minimum sample split part, where you are saying that the minimum sample leaf, you are specifying the minimum sample leaf, right? That this is the minimum number of records which will be there in my sample. So let's say the minimum sample leaf, I keep it at 6. Let's go back to the previous one. So previous one, in a particular node, I am having 12 records, which is fine, right? It satisfies my minimum sample leaf, which says 6 records needs to be there at least in a particular leaf node, right? So then this satisfies, so I can split further. So in one side I get 8, and the other side I get 4. So 8 is fine. 8 satisfies my minimum sample leaf because my minimum sample leaf is at 6. So 8 satisfies that. The other one, which is 4, 4 violates my minimum sample leaf. If 4 is violating my minimum sample leaf, then this particular split becomes invalid. The split exactly becomes invalid. So I'll probably go back to the previous one. I'll say that, okay, this is where I should be. I can't split it further because it violates my minimum sample leaf. So these are also some of the hyperparameters which are being used in order to ensure that you don't get a overfit kind of thing. This is also something that you use. Right? Okay, so this is the example which I was talking about. Right? Okay. So again, how we are going to optimize this again? We are going to do the hands-on. The hands-on class will do some examples of decision tree and all the other parts. But yeah, this is where I would like to keep the session for the day. Tomorrow we are going to talk about this machine learning model fitting, right? How do we fit a machine learning model? What parameters we take? So that is going to be our agenda for the next class. And then the class which is there next week, that agenda will be on ensemble method. And the last class we are going to do the hands-on part. That is how this plan. Yeah. Any questions before we call it a day? Any questions? Right? I know it's already late in the night. Right? Questions? Questions? I don't think I have this thing. My bad. No one mentioned also. No one mentioned also. I could have just shown you the slide. Just a moment. I think I stopped doing it. Okay. Yeah. This was the criteria, right? The entropy, Gini, maximum depth, things. I think there's some questions. Some questions also. Oh, I could. Yeah. My bad. My bad. Sorry, Sambit, Shika, and all the other people. Right? Sorry, my bad. Your notification didn't come up. Right? Yeah. So this was some of the pieces which I was talking about. The split criteria, maximum depth, minimum sample split, and maximum sample split. Yes, let me just repeat the minimum sample split part. So let's say that I am having 12 records, and the minimum sample split has, let's be set as 10. Right? So my 10 is less than 12, right? Rather the other way around. So this 12 is greater than 10. So fine, I'll be able to do this minimum sample split, whereby let's say one split is 8, the other split is 4. Right? So it satisfies the minimum sample split part. Come to the other one, which is the minimum sample leaf. So let's say that I have kept the minimum sample leaf at 6, which means what? That there should be a minimum of 6 records at a particular node. So in the minimum sample split part, first of all, this one. So after splitting this node 12, it gives 8 and 4. My minimum sample split is set as 10, right? So now when it is 8, so 8 is less than 10, right? So I can't split this further. 4 is less than 10. this one also I can't split further. Right? So this is probably where I would stand by. For the case of the minimum sample leaf, it has been given as 6. So which means that in a node, there should be at least 6 records for it to be eligible for splitting. So here, 12 records I had. So 12 is more than 6. So I can do the splitting. And after doing the split, I get 8 here and 4 here. Now 8 is greater than 6, which is fine. So this one is fine. But 4 is less than 6. So this becomes invalid. So this whole split itself becomes invalid. So at this particular level, I am not able to split further. I have to remain stuck in this particular level only. Right? That was the minimum sample split and the minimum sample leaf. Right? And this is how it runs, right? Maximum feature, minimum sample split, right? All that fun. And I think people had some questions. So first I will come to Shikha. Yes, Shikha.
Yeah, thank you, sir. So if you can just go back a slide where you were just showing minimum sample leaf split, right here. So you said that at the end that 4 is less than 6, so this cannot be split, but 8 and 8 is more than 6, but this entire thing cannot be split because 4 is less than 6.
Right.
If say 4 is already homogeneous at this point, which anyway we don't want to split, and we only want to split 8, we can still do that.
No. So this particular, if I apply the minimum sample leaf criteria, which says for any particular node to split, right, there should be at least 6 records. Right? I'm sorry. If I do the minimum sample leaf, so minimum sample leaf says that the minimum number of records which should be there in a leaf node. So here, in one case, the leaf node is having 8 records, which is fine because 8 is more than 6. In the other case, it is 4. Right? But 4 is less than 6. So this particular node itself violates my minimum sample leaf condition. I can't have this configuration altogether. If it was 6, it was valid. But because it becomes invalid, then this particular split itself becomes invalid. So I'm going back to the part where there were 12 records and I'll have to remain at that.
Okay. So even if 4 is a homogeneous, anyway, we don't want to split it further. There is no way we can sort of set that, you know, we only want the minimum sample at the leaf node to be 6 if it is not homogeneous or something like that.
It doesn't work like that.
No, it doesn't work like that.
Then probably you'll have to do some kind of a further, so that will be again some kind of a re-engineering on the algorithm itself, which you can do.
Right.
But again, that is more re-engineering.
Yeah.
So rather than that, what you can do is you can just change the condition of the minimum sample leaf.
Yeah, of course, to less.
Saying that, okay, so let's change this to 4.
4, yeah.
Then
and then it gets split. Yeah.
Right. And the other is this minimum number of minimum sample split, which tells you that how many samples should be there at least for you to be eligible for splitting. So here I've given 10, so 12. It is eligible for splitting, but again after splitting it becomes 8 and 4. So none of them is eligible for splitting, but it's fine. This particular configuration can stay with the minimum sample split at 10.
Right. So, sir, so when you say that when we change the minimum sample leaf to 4, and now this is valid, and again the question stands that if 4 is at this point homogeneous, the algorithm will not split 4, correct? It will only split 8.
It will only probably split 8. Yes.
8, yeah. Okay, right. The second question I had was regarding one of the questions that came today in IA. It was theoretical. It was an MCQ, but maybe in the next session you can address that if it is a lengthy discussion. The question was that the decision tree is, it was a true or false question. The decision tree is what was it? Spatial, makes general assumption about spatial distribution and classifier features, something like that, which I completely did not understand the statement. So if you can talk.
I also don't remember the question, but whatever you're saying, it probably points to the particular part when we have discussed, like see, for example, your decision tree, it's a non-parametric method. So non-parametric in the sense that it doesn't make any kind of assumptions about the underlying spatial distribution of the data, right? See, for example, your linear regression. The
Yeah.
underlying assumption is that the distribution should be linear in nature. So in that
I
way, the
see.
tree doesn't make any
Assumptions.
I think that is probably the question that you are
Right. So yeah, something similar to that. And then there was second was like the same thing, general assumption about spatial distribution. And the second feature was, I think, classifier feature.
I frankly don't have the questions or to remember
Right.
them.
Right. I'll exactly pull out that statement in a minute. I can
Okay.
probably put it in the chat when I'll find out.
Yeah,
So when
yeah.
you talk about parametric and non-parametric, how do you classify that, right? About how do we know one is parametric or one is non-parametric?
No, it depends on the this thing, on the nature of the algorithm itself. See, for example, your this thing, your
Linear regression is parametric.
it's a parametric method.
Okay. No, I mean, what makes it? Because it makes some assumptions. That's why it's a parametric.
It makes some assumptions about the underlying distribution of the data set.
And what about KNN? Is that also parametric?
No, it's
No,
not.
it's a non-parametric.
It's a non-parametric.
Because again, there is no assumption made. It makes a
assumption made.
calculation.
Yes.
Okay.
Can
All
have
right, sir.
that way.
Thank you. Those are the questions I have.
Okay. Sambit, I'll come to Sambit. Yeah, Sambit.
Professor, can you share that previous PPT which you are showing? Actually, that was not shared to us.
Which one? Which one?
Just from where you are, yeah, from where you are giving us that. No. That this part, entropy and all part. That PPT was not shared to us.
This PPT was not shared. How come?
Yeah, I'm not able to find this.
This is probably the first or the second. It should be there. Please let me know tomorrow if it's not there.
Yeah, because some part are there and some part are missing. So I was just checking some few of the things, so I'm not able to find it.
Okay.
Yeah.
It has been shared. I think that's what Shukant is saying. Just check. I think it should be there.
No, it is shared, but all the content which was there here, right? It is not there. Yeah.
Not sure. This problems. So we have done. I mean, the same problems.
Yeah, problems are there.
Yeah,
some slides are missing. That's what I want to convey.
Let me check once again. Again, it's not about the slides. So sometimes what happens is when people ask some questions, so I have so many backup slides, right, for every topic, right? This is what I
Okay.
So sometimes I pull those up. But again, whatever is important has already been shared, right? Don't worry about that part, right?
Okay.
Okay. Fine. So let's call it a day. I think I have overshot this thing, but again, it was a good discussion. Many good questions came up. So yeah, we'll meet tomorrow, and tomorrow's class we are going to discuss those parts of this thing, the model fitting part. Right? How do we ensure that a model is a good fit or not? Fine. So that's it today. So thank you everyone. So we'll meet again tomorrow morning. Good night, everyone.